combining distributions. It's the second thing, and it comes very much off the back of the tables and the random variables. In terms, the discrete random variables, in terms of the formula sheet, the material for the first lesson is there. What we're looking at comes under this business of expectation algebra. It's not a really common question. If you look at the distribution of the questions, there's always something about the expected value in every exam, pretty much, using the tables almost always. But sometimes, and more recently, there's been these ones of combining different variables together. And there was a classic example in the sample paper, but they never really followed up. So there is some fixed rules for expectation and for variance. For expectation, if we've got two distributions and we join them together, the means just get added. If we multiply one of the variables and then add a fixed number to it, we do the same with the means. Now, these formulas in their raw form don't make a whole lot of sense. The ones to watch out for are the variance. And the trick is this line here is probably the key one. If we have a random variable like the dice game that we looked at last time, and we multiply it and then we add in value, so we might be looking at winnings or something like that. If we add a value to every value in our options, so our table, if we think of this in terms of a table, we just add 5 to everything. It actually has no impact on the spread. And so you'll notice with the variance, the plus b, which would be like adding 5, doesn't get any mention. But what happens if we multiply all those winnings by doubling them or something? It actually has more influence on the variance. And so if we doubled them, we would go 2 squared times the original variance. And that's something we'll do an example for each of these. And for the variance, whether we're plussing or minusing, if we're combining any, it's always adding variation to the total. Whether we add or subtract, both random variables bring extra variance to the game, if you think of it like that. So, got a practical example, and these facts hold true for all three. So if we've got a repair job for washing machines, expected cost for parts is $2.40 with a variance of $60. And the expected cost for labour is about $3.60 with a variance of $40. So, and there's a setup fee of $60 for the job. So we've listed the keys. So the expected for parts is that, the expected for labour is that, the variance for parts is that, the variance for labour. I could add a standard deviation to it, but we'll deal with that at the end. And so what is the expected cost and the standard deviation of the charge for one machine repair? So the cost is, you've got your parts, you've got your labour, plus your $60 setup fee. There's like a call out fee. So parts plus labour plus 60. What does that do for in terms of expected value? Is very predictable. 240 plus 360 plus 60. So we expect the job will cost $660. And you don't need a formula to tell you that, really. Where it gets a bit more murky is the variance. The variance of parts plus labour plus 60. First thing to note is the 60 doesn't affect the variance, so we can ignore that. So in that case, we've got the variance of a couple of things added together. What do? We combine the variances. So that would be the 50 plus the 40. And so we've got a variance of 90. If we want to calculate the standard deviation, which has more meaning, because variance of 90 is actually ridiculously large, the standard deviation is the square root of the 90, which is 9.47. So we've combined two variables and a fixed charge. If we go to another situation, Renee was washing a brand that's known to take double the time, so they're shocking. So the labour tends to be twice for this. But everything else is the same, the parts and the starting fee. What would the expected cost and standard deviation? Now the expected 240 for the parts, 2 times 360 for the labour because it's niggly, plus the standard 60. So we expect the job will cost $1,000, $1,020. For the variance, again, the plus 60 is not a factor, so it doesn't pop up. The variance for the parts should be a 50. I'm looking at that. So I'll change that as I go. Now, 2 squared times the 40, and this is this rule cutting in. If one of my variables is multiplied by something, I take the multiplier and square it times the original variance. So I will have to have 2 squared times 40. So that's 4 times 40 is 160 plus 50. I'm going to have to make an adjustment. This will actually be 210. Okay. And then when I square root it, this value is going to be wrong. So I need to square root 210. So I need a calculator. I'm going to do this on the fly, which is bad form. Square root of 210, 14.49. So it hasn't changed it too greatly, to be honest. But we'll fix that as we go. So the key thing there is that 2 squared times the variance. The 60 disappeared again. Now, changes slightly. If Diane wants to buy the parts for 2 repairs and do it herself, what would the expected cost be? Here, the expected cost, 2 lots of parts, $480. Nothing too surprising. And in that case, the variance plus the variance is 100. And so the standard deviation for the cost for that job would be $10. So the expected cost will be $480. Standard deviation of the cost would be $10. And these questions come up just in a few spots. It's not one of the more common ones, but often tacked on, and it's shown up in 2 or 3 of the last 3 papers. 2 of the last 3 papers. So worth having a bit of a look at.